There we go.
Hello, everyone, and welcome for this last tutorial slash educational workshop of Maine. This is so sad, but we're going out on a fantastic note because we're lucky to have Pamela Douglas with us. So Pamela is currently an assistant professor at the University of California in Los Angeles, as well as the University of Central Florida, and this is not a glitch, she's at both location. She completed a PhD in neuroengineering at UCLA, during which time she worked in the Cohen Lab at UCLA Center of Cognitive Neuroscience. She utilizes machine learning algorithm for classifying functional neuroimaging data and as a model for computation in the human brain. Her interests lie at the interface of applied mathematics and neuroscience, and she seeks to apply the most advanced concepts in pattern classification to the exceptionally challenging task of understanding the human brain. And I mean, in the previous tutorial with Jessica Thompson, if you were there, we've heard a lot of interesting things about interpretability, but at a quite a conceptual level. And I think Pamela is going to tell us a little bit more concretely when you try to tear apart a system, even as simple as a linear system. Can you really make sense of their parameters? Is that straightforward? So I think it's a wonderful complementary view on interpreting machine learning tools that we're having today. And without further blah blah on my part, please, Pamela, take it away.
Yay! Thank you so much. I'm so excited to be here. Maine is such an amazing event, and yes, so sad that it's coming to a close. But yes, so I'm going to just talk a little bit about an introduction to interpreting deep learning models. So I've been involved in this business of decoding and neuroimaging and applying deep learning for group membership classification for quite some time. So here's a few examples of some of the things that I've done over the years with some amazing colleagues. So predicting, for example, an ADHD diagnosis using functional modular organization, and of course, replicating this in a few different studies using a variety of connectivity measures. Also predicting autism spectral disorders with functional connectivity, predicting a variety of different types of belief and decision-making from religious to autobiographical using independent component features, and recently this year predicting empathy from self-other resonance networks. So with deep learning, you've been hearing about quite a lot. You know, we start with some training data like pictures of dogs and mops, for example, and we send this through our deep learning model, and assuming we've done our due diligence, we have we've tested out a variety of different models, and we get some sort of accuracy at the end from the training data. And then, of course, we want to be sure that we don't have any sort of peaking or circular thoughts. So then we test on a separate left out example, and then we send our test data once again through this black box, and something happens, and yay, we find out that it works. So that's exciting. But there's this question: why do we actually care what's inside? So if it's working, what is the point of peering inside the black box and trying to make these methods transparent? So there's quite a few reasons for, or different motivations for, developing explainable AI techniques. So one of them is, of course, to verify fairness. So to make sure that our models are avoiding perpetuating demographic biases and inequalities when we're deploying our technology. So here's a few examples here from predictive inequalities in detecting pedestrians of different skin tones. And then this other fun article, Women Also Snowboard, Overcoming Bias in Captioning Models. And it turns out that many models actually seem to exaggerate biases in the data. And unfortunately, in some cases, balanced data sets are not enough. Again, before widespread adoption, we want to make sure that our deep learning models are reliable. So to ensure that the model is robust to adversarial examples, noise, and perturbation. So these adversarial examples could be designed for malicious purposes, or they could just be random variation that we have in the environment. So adversarial examples in the wild. And this is this fun example from Evtimov, who studied different graffiti on different stop signs and how that would affect self-driving cars. So another thing is that model transparency helps build trust. So part of building trust is helping the user identify points of model failure and verifying that indeed there was a proper problem representation and ensuring that the model has learned the intended concept. So below here are some examples of the model being wrong or right for the right reasons or right for the wrong reasons. And so we want to make sure that our model is right for the right reasons. So ultimately, we essentially wish to ensure that the input pattern that we think is important does in fact serve the expected function to convey information downstream and to avoid overinterpreting our features or feature fallacy. We also want to ensure that our model is not operating on spurious correlations. And so there are actually many, many examples of spurious correlations that turn up. And here's some fun ones. In case you haven't been to Spurious Correlations, this website, there's quite a lot of fun examples. Looking at, for example, the number of films that Nicolas Cage appeared in, and the number of people who drowned by falling into a pool or by becoming tangled in their bed sheets. So we don't want our model to be operating on spurious aspects of the data that could be randomly correlated with the goal of the model. Another nice thing about transparency in deep learning is that it helps keep humans in the loop. So this is an example I really like. My brother is a radiologist, and he was taught that the only thing that really mattered when examining a tumor in order to do tumor staging and predict outcomes was the borders of the tumor, similar to, I think, skin cancers as well. But recently, convolutional neural networks based on texture features have been able to find that indeed there is diagnostic or predictive information within the tumor border itself. So in this sense, deep learning, if it's used in a transparent fashion, not only keeps humans in the loop, but it may be able to teach humans different and new information. So in that sense, it may also be used as a tool for exploration. And there's many, many, many explainable AI techniques at this point. And what's amazing is that most of them have a common goal, but they seem to take a variety of different divergent approaches. But there are indeed different questions that they ask. So for example, archetypal methods ask this question: what is a prototypical example of Y, of the output? And so some examples of this are activation, maximization, which searches for input patterns that produce a maximal response from the model, or generative methods, such as generative adversarial networks. But what I'll be talking about mostly today are these methods called post-hoc relevance methods that essentially investigate which aspects of the input X provide evidence for a particular output Y. So another question we might ask are, what are some desirable properties for explainable AI techniques? So here are a few. First of all, we want our explanation model to be sensitive. So we want it to be able to predict input variables that are important or relevant for model predictions. There's also this idea of completeness. I like to think of it a little bit more as conservation. So it's this idea that the sum of all relevant scores should equal that more or less or approximately of the output. There's also this idea of input invariance. So essentially input invariance is this idea that the saliency method should mirror the sensitivity of the model to the input perturbations. And lastly, format. So we want our explanation methods to provide explanations in a format that can be digested and understood by a human. And so there's kind of an intuition that we're going to be showing an image with some sort of a heat map or a saliency map, but that's really just within the visual domain, and trying to figure out the correct format in other more complex and multimodal domains is still a little bit of an open question. So one of the simplest methods for this post hoc interpretation is just a simple sensitivity analysis. So with sensitivity methods or occlusion methods, the most simple probably being just a simple pixel flip, the question is, how do these small input perturbations alter the model performance? And so the idea is that you search over the space and determine if that specific pixel was important based on the amount of accuracy drop when you eliminate it. So the problem with sensitivity methods like pixel flips and occlusion techniques is that they actually often miss information. Another problem is that a simple technique where you take the gradient and you multiply that by the input, those are actually going to fail input invariance. So this is a really nice study by Kindermans where he took a specific model, 2 different networks, where all that was really altered was the input was shifted. And so the networks had the exact same input-output performance, and they also had the exact same gradients. And it turns out that this gradient by input is going to give you a different explanation, even though the network has the exact same attribution. So in that sense, it's possible to alter the explanations without actually altering the predictions. So you may get the exact same accuracy, but just this simple input shift can actually cause a variety of differences in the heat maps themselves. Another thing that's been pointed out by Smilkov et al. In 2017 is that the problem with multiplying your gradient by the input is that it also forces any 0 pixels to have 0 attribution, which may or may not be the case. Another issue with these simple methods is that dropping a pixel or dropping a drop block, for example, that sort of falls into this category of regularization methods, because sometimes adding noise or stochasticity or perturbing your input can actually boost the performance of your model. And so one of the reasons that can happen is if you're blocking out a redundant set of features, sometimes it just causes your model to be more parsimonious and more sparse. And that may actually boost the accuracy, even though that set of features is actually informative for the output. And so this is, of course, an issue because the perturbation methods are actually evaluated based on the drop in accuracy due to that specific perturbation. So this is quite similar. Pierre brought up the linear case. So this has actually reminded me of the linear case, where it turns out if you have voxel selection by L1 penalty on brain maps, it's unstable because neighboring voxels that are typically fairly redundant respond similarly. And these L1 estimators will choose somewhat randomly few of these correlated features. So you may get a boost in your accuracy by having a more parsimonious model, but it actually eliminates and makes it, in some sense, more difficult to actually interpret. So there's also these nice techniques called redistribution or decomposition techniques. And these are a way to calculate a heat map or a saliency map by starting with your output after you've trained the model, and then redistributing the saliency backwards through the model until you reach the input layer. And so relevance redistribution methods, the first step is to train the model using backprop or similar on, of course, your training set. So this is essentially called the forward pass. And then afterwards, we have a test example, and we redistribute the relevance backward through the model. And that's the relevance propagation reverse pass. So 2 examples of this redistribution or decomposition are the deep Taylor decomposition, as well as the layer-wise relevance propagation technique. So the LRP method is typically implemented using this alpha beta evidence rule. And the idea is that there should be a conservation of relevance for each layer and across each layer. So the sum of the relevance at each layer should be equivalent. So LRP, under certain conditions, can be viewed as a subset or subtype of a deep Taylor expansion through the layers. But one of the problems that you may run into using these redistribution techniques is that they actually require tuning of hyperparameters, and the hyperparameters help find the root node or the reference point. And so depending on what your reference point is, these attribution techniques may or may not fail input invariance. So unless in this study, pattern attribution was the only method for incorporating covariance structure into the data, which then helped determine the root node. But in most of these cases, for example, the deep Taylor decomposition LRP method, you can see that adding this constant shift to the input of just the MNIST data caused different attributions between the two networks, despite the fact that, again, they had the same input-output mapping and the exact same gradients. So the other thing is it's unclear if these provide a unified explanation or all relevant features. So how do we verify or quantify the quality of our explanations? So how do we verify the methods that are used to verify the model? How do we quantify the quality of the explanations? So two ways, which are discussed in this nice Osman paper from 2020, are relevance mass accuracy and relevance rank accuracy. So these two methods work very well for quantifying essentially how well the explanation map overlaps with the map of ground truth explanations. So these are kind of similar in some sense to sensitivity and specificity that are commonly used in the medical imaging world. So that's an excellent way to quantify the explanations if we have synthetic and benchmark data. But what if we don't know what the ground truth is? If we don't know what the ground truth is, how do we actually quantify how well our explanation is overlapping if we don't have the ground truth? So this is just an example of some work that I did with Farzad Farahani. And we were interested in trying to examine the old ADHD 200 data set, which was a data set of 776 labeled brains from 6 sites and 200 unlabeled brains from 7 sites. So because there was an additional site that you didn't have training data for, this problem required some transfer knowledge. So my team we extracted all these different features because back then we thought that you needed to extract features from the functional imaging data, from subcortical and cortical morphology measures to functional modular organization and graph theoretic measures. And what we found was, again, that we had really quite nice predictive accuracy within a site, but the transfer learning was very difficult. That was a very difficult task. And some follow-up work that I've done along these lines is examining the morphometry of changes across the lifespan with the Enigma group, as well as between ADHD individuals and typically developing controls. And what the two brain structures that typically come up as being important across the lifespan are the caudate and the amygdala. And so what is kind of amazing, as an aside, about this study is that it turns out that later in life, it almost looks like ADHD may be neuroprotective. So say after the age of 50 or 55, the estimated volume in the ADHD brain seems to be declining less. So we wanted to revisit this ADHD 200 data set but use explainable AI techniques to help us get a deeper understanding of what parts of the brain were informative for an ADHD diagnosis. And we wanted to verify that our methods were working. So we got some inspiration from this very famous study, of course, now from Goodfellow, where they perturbed images by adding some noise, which was along with the sign of the gradient. And what's kind of amazing about this paper is, to me, I can't actually personally tell the difference between the panda on the left or the panda on the right, which was, of course, after this small amount of noise, assigned the label gibbon with 99.3% confidence. So the confidence actually went up that this was a gibbon. So to me, that on some level suggests that we may yet have something to learn from the human visual system, because it seems as though something about the human visual system confers a resistance to, or some sort of fault tolerance to, adversarial noise. And we were also inspired by, of course, this also very famous paper that appeared at CVPR a couple of years ago, where they discovered that this classification of horses was relying heavily on a spurious correlation of this copyright symbol here. So combining those two, we decided that we wanted to take our data set and perturb it with, first of all, adversarial noise that is in the wild or common to the MRI setting. So it turns out that Rician noise is very common in the MRI setting. And we also, so the noise was going to perturb the model to see if we had different, not only different predictions, but also how reliable our explanations were across adding noise that is common to the MRI setting. But we also wanted some subset of features or some pixels that would actually serve as a benchmark in some sense, a benchmark didactic example. And so that would provide evidence for a true positive. So sort of like in biology, where you have a true negative and a true positive typically built into your experiments, we wanted to build that in as well. So what we did was we took pandas, little tiny pandas, and we put them in the upper right corner of the brains that had ADHD. And so in theory, that little upper panda was 100%, and we varied it across which percentage, but in most cases, it was, in the first case, it was 100% correlated with the class label. So that little tiny panda image served as a didactic teaching signal for the model. And so what we found is that when you vary the amount of subjects with the noise, which might happen if, say, you were scanning at 2 different sites, when all of the subjects were corrupted by noise, it seemed as though the model learned the noise. But when somewhere in between 0 and 100 were affected by the noise, we did in fact see a drop in the accuracy. It's also worth mentioning that on just the images here, and we took a slice that maximally showed the amygdala and the caudate. So just those 2 slices, actually this performance outperformed our handcrafted features from the original ADHD 200 competition. So that was kind of nice. And we did test out a few different models. We found that an 8-layer CNN worked the best. And then instead of using relevance mass accuracy or relevance ranking, we came up with this thing called relevance structural similarity analysis, which is just essentially a distance metric for images, because we wanted to determine how different our output explanations were using a variety of techniques. So we tried out layer-wise relevance propagation. We also tried out Lime. Since this time, we've also tried out pattern attribution. And it turns out that in almost all of the cases, the didactic panda was missed. So I guess in some sense, that's kind of encouraging that, in fact, aspects of the brain are more supportive or provide more evidence for an ADHD diagnosis. But the fact that the panda was missed is somewhat problematic if what you're looking for is a full unified explanation of all of the pixels that might be important or informative for a specific diagnosis. So that would, of course, be the case if you're trying to examine brain tumors. You wouldn't want the model to say, okay, just resect a small portion of the brain tumor. You would want to get the entire tumor. So in that sense, these techniques did not provide a unified account or an unabridged account of all of the important pixels for prediction. So there's also this functional interpretation. So functional interpretations or functional approaches examine the learned representations in the graph to try and reveal or understand some mechanistic aspects of the algorithm. So part of the inspiration for this type of interpretation is that, of course, neural network models like brains can perform feed-forward computations like within the cerebellum, recurrent computations like the cortex. They typically have a large number of weights or parameters because intelligent systems are expected to require ample knowledge and sufficient capacity to store and manipulate information. So perhaps neural network models can serve as a brain computational model to predict brain activity data, human behavior, and accomplish tasks all within the same model. And so there's a lot of evidence that indeed neural network models seem to be an excellent, if not the best working model for internal representations within the human visual stream. But one caveat to this is that, for example, if you just see Gabor-like features learned in your input layer, that might be a necessary, for example, condition for you to say that this is a good model of the human visual stream, but it should not be sufficient because, as it turns out, many different types of deep learning models and different architectures also have Gabor-like features in the input layer. So in that sense, it's always a good idea to test out multiple models because of this thing called single model fallacy. Even a bad model can explain some variance of the data. And sometimes there are many equivalent good models. So sometimes it's hard to perform model selection, but it's always a good idea to test out multiple different models, or in some cases, multiple different families of models. So just to summarize the results from the didactic and adversarial examples in the wild, the relevance maps generated using the layer-wise relevance propagation methods seem to be the most stable across noise perturbations typical of the scanning environment compared to other methods. However, none of the methods provided a unified explanation in that they assigned zero weight to our didactic perturbations in the form of a panda. And probably because the panda, or the lack thereof, was redundant with its counterpart, for example, in the balanced, typically developing data set. So here are some summary and thoughts and conclusions. So, of course, great care should be taken when interpreting, encoding, and decoding results, even in the linear case. It's almost always a good idea, I can't think of any reason why not to test multiple models, because this idea of no free lunch apparently still applies. And because testing only a single model may just simply be confirmatory in nature. Transparency methods for deep learning is most certainly an active and I think somewhat nascent field of study still. It's still a growing area of study. And we are definitely in need of more complex synthetic benchmark data sets for explainable AI, where the ground truth is known and it's not just a simple data set, it's a more realistic, complex data set. And of course, having true positives and true negatives built into our benchmark data set is most certainly a very important aspect of creating an important and meaningful synthetic data set. And one alternative, perhaps, to having a benchmark data set itself is to possibly having benchmark data perturbations, such as adversarial noise that you might find in your particular data set, or didactic perturbations that help serve as a positive control for your explainable AI experiments. And hopefully these can help one day move towards a unified and sensitive and specific model that also can be verified with these explanations. So thank you all so much. I really appreciate your time, and it's so exciting to be at Maine. It's so exciting. So thank you so much. And I guess I'll take questions now.
Absolutely. Thank you, Pamela. Wonderful presentation. And yes, we do have a number of questions which have been upvoted on by the viewers, and I hear something else. I don't know the sound. Okay. Yeah, there's been a lot of conversations about dogs and pandas in the chat, and I apologize for the viewers who got a little bit confused by this. Those are the sort of like, imponderable, unavoidable facts when you do something live. So pandas, dogs, pandas, but we have actual scientific questions as well. Question number 1 by Dora. Don't you think at least what is partly different in human versus models with regards to noise resistance is the fact that number of units, the neurons, in the brain processing a given unit in the input pixel is much more, even in several orders from the number of units in an artificial neural network. So to rephrase that, we've got much more neurons in biological brains than in artificial neural networks, which may explain their behavior regarding noise perturbations. What do you think of that?
Yeah, I think that's a great thought. I think that's a really interesting possibility. I don't think I know the answer, but I think that most certainly one thing to think about is the extent to which our models are using distributed versus symbolic representation, because architectures that use symbolic representations tend to be more resistant towards, they have more fault tolerance against adversarial noise. So I think that's most certainly something to think about. Although I don't know that there's any evidence per se that the human brain uses that. Maybe there is something at the detection level, for example.
Absolutely. I mean, it's a great hypothesis. I just like to point out that also the sort of sheer volumes that biological networks are exposed to of data is incredible. Like when we think about ImageNet as a fairly large data set, millions of images, if you think about human perception, the vision domain, we're perceiving 30, 60 images per second, maybe even a little bit more than that. So that means that in a few days, we see much more than ImageNet. And, we live for a long time, plus we have evolution behind us. So, we have lots more parameters, but also much more data condensed inside our brains.
Yeah.
So,
yeah, that's a great point. We've had training data since we opened our eyes. So
even before, we react to different types of languages through exposition in utero. Like it's we're fed a lot of data. All right. So other question. Given how before I move to question number 2, before I forget, please don't leave at the end of that session. I said this was the last session. I was right, scientifically speaking, but we have a goodbye session right after that. Please join us. We're going to have, folks from the organization, different folk from the speakers showing up and do a little celebration. So please join us if you can after this particular workshop. Back to the questions. Question number 2. Given how the human brain is a reason for current biases, shouldn't we depend more on non-human brain inspired methods to avoid such biases? can we skip human-inspired methods entirely, or data set, I would guess.
Fascinating. That's a really good point. I mean, I'm not sure. I'm not sure how to answer that.
I'm not sure to fully understand the question either. Mohammed, who asked the question, added this specification. I mean, in application when this actually matters. So I would guess, in I have to say, so Pamela, help me out here. I'm or if anybody in the audience want to bring some elements, because I'm not sure I understand concretely what we're talking about here. What would that mean? So, if I imagine a vision system that would recognize people susceptible to be bringing weapons on planes, and you tag it, and you somehow end up tagging a lot of people with certain characteristics, and that very damaging to this population. How would you use non-human brain methods to deal with that? I don't know, maybe bring a dog data set in the fold.
Yeah, I'm not sure how to correct the methods, because I think what they're saying is that humans in the loop is the problem in the first place.
Yeah.
And so if you bring humans into the loop using these explanations, is that not just simply going to further perpetuate the bias that humans introduce? Because the models are, of course, known to exaggerate the bias. Not all models, but some models tend to exaggerate the bias. And that's part of how they learn. So,
I mean, so Mohammed in the chat added a sort of comment. All we do results of human thoughts, so there's human bias throughout. Several people do the same point in the chat. I mean, yeah, maybe we could have annotations generated by other species somewhere and get a different kind of bias in our data set in the fold. But I think we can move on to the next question. So the pervasiveness of human biases in everything we do. So question number 3, what are the considerations for the end user, such as health professionals, when designing explanatory methods? So I think, a critical question when it comes down to practical usage of deep learning models. How do we take the practitioner viewpoint?
Yeah, that's a great question. I think it's going to take a few iterations before we actually know the true answer to that. I think, like I said, I guess at the beginning, one of the things that I brought up is that in medical imaging, we're dealing with images. And so, of course, mapping the explanations to the images is one of the goals. And then you have these, heat maps or saliency maps, attribution. But how do you present information when we start to have lots of multimodal data, or from auditory signals, for example? So I think it's going to take a few iterations of human users providing feedback to the XAI developers before we converge onto something that's more useful for the end user.
Thank you a lot, Pamela. I'm trying to monitor in parallel in the chat to see if there's some follow-up, but I think we can move on to the next question, because I'm just also keeping a little bit of an eye on the time. But we had an hour for this session. We had a little bit of a buffer, so we can keep going. And there are more questions. So what are the considerations? Oh no, this one is completed. Sorry. Have you tested Shapley values, which I think is actually spelled SHAPLEY, as a measure for explainability in your model? What is your opinion about it? So, Pamela, do you have opinions about Shapley values?
I do not have strong opinions. I've come across them, but I have not tried them out myself, so I don't know.
So we only have second-hand opinion on Shapley values to express on this session. If anybody in the audience has a strong opinion on Shapley values for model interpretation, please do not hesitate to share them in the chat. And on that note,
someone says, I accept all cookies.
Somebody said that too. So that's another attempt to confuse our audience. After the pandas and the dogs, we now have cookies. That made for a fun session. Thanks again for joining us, Pamela, today. Thanks to everybody who joined us to follow along for that educational day at Maine. And as I mentioned, we are going to have another session in a few minutes at 4:30. It is currently 4:28 Eastern Time, so in 12 minutes, where we're going to bring everybody to say goodbye and celebrate, as we should, the end of that Maine 2020 event. So thanks again, Pamela. See you soon.
See you soon. See you in 12.